Today's modern microchips, GPS systems, and electron microscopes all rely on a single string of mathematics from 1925. Erwin Schrödinger formulated this wave equation to describe the hidden mechanics of atoms, and it remains the primary tool we use to engineer technology at the quantum scale. Yet right at the front of this equation sits I, the square root of -1, an imaginary number. Physical objects like computer chips and electrons have real, measurable mass and energy. Calculating their behavior should not require a theoretical number that doesn't actually exist on a standard number line. To see why Schrödinger was forced into this corner, we have to look back at how physicists pictured atoms. They originally imagined electrons orbiting a positive nucleus, like planets around a sun. But orbiting charges accelerate, and accelerating charges radiate energy. Under that model, every electron should quickly drain its energy and spiral into the nucleus. Atoms would collapse instantly. A physics student named Louis de Broglie proposed an alternative. He suggested that matter behaves as standing waves. Instead of a tiny marble circling a track, an electron is more like a continuous guitar string. It can vibrate in fixed loops around the nucleus without moving from point A to B. Because standing waves do not accelerate, they never bleed energy. This solved the stability problem. But if electrons are waves, physicists had to figure out how to mathematically map their energy and momentum. Schrödinger attempted to build a wave equation using the standard math of periodic waves to solve this problem, but he quickly found it was logically impossible. The engineering challenge is straightforward. We need a mathematical operation that pulls the momentum variable out of a standard periodic sine wave. If you want momentum, you take the second derivative of the wave function. The math cleanly separates out the momentum value, and more importantly, it returns the function back to its original sine wave shape. We get our data out, and the wave remains intact. To extract the wave's kinetic energy, however, we only need to take the first derivative. When we apply a single derivative to a sine wave, we get the energy variable, but the wave itself changes shape into an offset cosine wave. We do not get our original function back. The math extracts the energy, but in the process, it morphs the electron wave into something entirely different, breaking the equation. To fix this, we need a mathematical function that doesn't change shape when you take its first derivative. Its derivative must equal itself exactly. There is exactly one mathematical function with this property, the exponential function. But using an exponential function creates an immediate physical problem. Exponentials either blow up forever to infinity, or they decay down to zero. A localized electron wave has to be periodic. It must oscillate consistently in a contained space. The math requires an exponential function, so we can calculate energy, but the physical reality of an atom requires a repeating, periodic wave. To write the code for the quantum scale, we have to invent a wave that is simultaneously exponential and periodic. By definition, these two concepts contradict each other. We can resolve this using a geometric insight from a 19th century accountant named John Robert Argand. He was interested in how you could visually manipulate exponential growth. If you multiply an exponential's velocity by -1, you reverse its direction, creating a bouquet. But we need a multiplier that takes the velocity and turns it perfectly sideways, perpendicular to its position. That specific 90-degree shift requires multiplying the exponent by the imaginary number I. Because I continuously pushes the vector sideways rather than forward or backward, it forces the runaway exponential function into a uniform, continuous circle. By inserting the imaginary number, the equation stays strictly exponential, allowing us to accurately calculate the energy. But geometrically, it spins infinitely in a perfect circle, satisfying the physical requirement for a periodic matter wave. For months after publishing his equation, Schrödinger tried to find a way to rewrite it without the imaginary number, hoping it was merely a temporary mathematical trick. The physicist Max Born realized why that geometry was strictly necessary. He proposed that the matter wave was not a physical ripple in space, but a distribution of probability. Born argued that if you take the amplitude of the wave and square it, you get the exact probability of finding the electron at that specific location. Since the wave dictates the probability of the particle existing anywhere at all, the total sum of that wave across the entire universe must equal 100%. Look back at the standard 2D sine wave we tried to use initially. As it oscillates, its amplitude constantly fluctuates up and down. Because amplitude squared equals probability, the total probability of the electron existing fluctuates too. As that 2D wave crosses the zero axis, its total probability drops to zero. According to the math, the particle would temporarily cease to exist entirely. Now compare that to our complex, spinning wave. As it rotates around the center axis, its radius, the amplitude, stays exactly the same. The probability counter remains locked at 100%. Because the wave constantly rotates in the complex plane, rather than passing straight through zero, the likelihood of the particle's existence is perfectly conserved over time. By forcing the wave to spin, it provides the exact mathematical geometry required to ensure the physical universe remains constant, preventing matter from flickering out of reality.